Okay, let's dive right back into this explainer. In part 1, we gave you the core vocabulary: PV, SP, OP, and MV. Today, we're going to turn those terms into the single fundamental error equation that drives every controller in the field. Plus, we'll look at the exact troubleshooting order every engineer uses when things go sideways. Let's get to it.
So just as a super quick recap of the 4 core signals in every control loop, first you've got your PV, the process variable. That's what is actually happening right now. Second, the SP, the set point. That's your target. Third is the OP, the output, the controller's command. And fourth, the MV, the manipulated variable, the physical equipment making the change, which is usually a valve.
Now here is where it all comes together. Error equals process variable minus set point. This single, simple equation literally drives every proportional, integral, and derivative calculation you'll ever learn in process control. And here's the absolute golden rule. Error is calculated in the exact same units as your PV. It just represents the gap between reality and your target. As that gap grows or shrinks, your controller instantly uses that numeric difference to figure out exactly how hard it needs to push the output. It is, without a doubt, the beating heart of the PID loop.
But wait, I have a massive real-world warning for you as you're staring at your screens and data trends. Please never assume that the electronic OP percent equals the actual physical valve percent open. Why? Well, because a sticky valve, a miscalibrated positioner, or even reversed action can completely alter reality out in the field. Think about it. Your controller's electronic signal has absolutely zero physical strength on its own, right? It relies entirely on an actuator. Whether that's compressed air inflating a diaphragm, an electric motor, or hydraulics, that actuator is the muscle fighting against process pressure and friction. So, if your controller commands, say, 47% open, but you've got heavy friction and no smart positioner, the actual valve could easily be sitting anywhere from 40 to 55%. Always, always verify with a physical or feedback check.
Let's look at a brilliant real-world example of this on an offshore separator. Say our set point is a 50% tank level, but our actual process variable is reading 48%. Using our equation, that gives us an error of -2%. So, because of that gap, the controller calculates a new output of 62% to open the level valve just a bit more. The valve physically strokes open about 2 degrees, draining or filling as needed, and the PV climbs right back up to match the SP. It's this continuous dynamic dance. The controller calculates the gap, adjusts the electronic output, the physical valve responds, and boom, the process variable settles perfectly back onto the set point.
All right, let's test this with a little interactive moment. Imagine you're in the control room. Your process variable is sitting stubbornly below the set point, creating this growing error gap. And in response, your controller's output just keeps climbing higher and higher and higher. The controller is practically screaming for action, but the PV isn't budging one bit. Think about the physical realities we just talked about. What exactly is going on here? Why is the loop fighting you? Well, if you guessed a mechanical issue, you hit the nail right on the head. The controller is doing exactly what it's supposed to do by shouting louder and louder. Its math is perfectly fine, but since the manipulated variable, the actual physical valve, can't physically keep up, you immediately know you have an equipment problem on your hands, not a tuning problem. The valve might be mechanically stuck because of process buildup, or maybe it's completely undersized for the current flow demands, or hey, maybe the actuator is just air-starved and lacking the muscle to push against the process pressure. The brain of the operation is fine, but the physical chain downstream just isn't delivering.
And this naturally leads us to the ultimate diagnostic flowchart used by pretty much every commissioning engineer in the field. When a loop goes rogue, you always want to troubleshoot in this exact order. PV first, then SP, then OP, and finally MV. Trace the signal path. Start by verifying the PV. Is the sensor actually reading correctly? Is there some false lag because someone forgot the thermopaste? Next, check the SP. Is the target even realistic? Then, look at the OP. Is the controller actually sending out the signal? And finally, the MV. Is the valve actually moving? I can tell you from experience, more often than not, the fault is at the physical ends of the loop, the sensor or the valve, and not the math in the middle.
So, you now know the essential control loop vocabulary and the all-important error equation. But I want to leave you with this thought. A basic home furnace and a massively complex distillation column both use this exact same vocabulary, PV, SP, OP, and MV, but they control that air in totally different ways. A furnace just slams a valve fully open or fully closed, while a column makes tiny, continuous micro-adjustments. Next time, we'll dive into the distinct styles of control that actually use this vocabulary, like on-off, modulating, open loop, and closed loop. Until then, ask yourself, based on the unique risks of your specific facility, which control mode actually fits your process best.